lecture we continue the discussion on hierarchical clustering, particularly the problem of forming part families. We then move to a non-hierarchical clustering algorithm. In the previous lecture we saw the hierarchical clustering algorithm, where given a machine component incidence matrix we could get groups ranging from all points or all machines in one group as one extreme versus each machine forming a separate group by itself. For example, if we look at the machine component incidence matrix given in the picture, there are 6 rows representing 6 machines and 8 columns representing 8 parts or components. So, we could, starting with the solution which has each of these machine as a group, we then merged the groups to get to a final solution which has all the machines in one group. We used the Jaccard similarity coefficient matrix which is shown here. Now, we said at the end of the exercise that if the user defines a certain number of groups, then we can identify the groups and give it to the user. So, let us assume that we have identified that we want 2 groups in the solution, and therefore, the 2 group solution from the hierarchical clustering algorithm is given here with 1 3 4 and 2 5 6. So, I am going to write 1 3 4 here and 2 5 6 as machines. So, there are 2 groups. The first group has machines 1 3 and 4, the second group has machines 2 5 and 6. So, we have formed the machine groups using this algorithm. Now, we have to form the part families. Now, the part families can be formed in more than one way. One of the ways is to look at the same matrix, and instead of creating a Jaccard similarity coefficient for the rows or the machines, we can create the similarity coefficient matrix for the columns or for the parts. In that case, we would have an 8 by 8 matrix and the similarities would be found column wise. For example, similarity between part 1 and part 2 would be similarity between this column and this column, which would be for part 1 the values are 1 0 1 1 0 1, and for part 2 it is 0 1 0 0 1 0 0 1 1. So, the Jaccard similarity coefficient for 1 and 2 would be the number of common ones which happens here. This is the numerator 1 by 1 2 3 4 5 6 1 by 6. Only one machine is common to both these parts. So, that comes as the numerator. Put together these 2 parts visit all the 6 machines. So, 6 comes as a denominator. So, the Jaccard similarity coefficient could be 1 by 6. Like this we can complete an 8 into 8 matrix and then use the same hierarchical clustering idea to make part groups, starting from each part as a separate group and finally finishing with all parts as a single group. So, there will be a solution for 2 groups. So, we could take that solution part wise and then we can easily find out whether that will go to this group, which one will go to this group and which one will go to the other group. That is one way of looking at it. But we are going to propose another way which is somewhat simpler and more or less as effective as the previous way. So, what we are going to do is we are not going to construct a Jaccard similarity coefficient for the parts. Instead, we are going to take each part by part and we are going to try and assign it to a known machine group. For example, if we take the first part, now the first part visits machines 1, 3, 4 and 6 from that figure. So, look at this 1, 3, 4 and 6, the first part should go to this machine group because 3 out of the 4 required machines are here. So, I will write part here and I will put 1. So, part 1 will go to this machine group because it has maximum number of machines required. And right away we can say that if we are assigning part 1 to this, part 1 requires machines 1, 3, 4 and 6. 1, 3 and 4 are here, 6 is here. So, we create one intercell move which is 1, 2, 6. If we had put part 1 here, then we would have created 3 intercell moves, which is not desirable. Therefore, we will put this part here such that it either has 0 or it has all the requirements, or it creates minimum number of intercell moves. We look at part number 2, which requires machines 2, 5 and 6. 2, 5 and 6 are here. So, part number 2 will go to this one. No intercell moves are created. Part number 3 requires 5 and 6. So, 5 and 6 are here. So, part number 3 will go to this. We also observe that part number 3 goes to this, does not visit all the machines, it actually does not visit machine number 2, but then part number 3 will still go here because part number 3 does not require any of these. So, part number 4 has 1, 3 and 6, 1, 3 and 6. 2 machines out of the 3 are here, 1 is here. So, part 4 will go here. So, part 4 will go here and it will have one intercell move with 4 and 6. So, let us write the second intercell move, which is part 4 to machine 6. Part 5 requires 1, 4 and 5. So, 1, 4 and 5. So, part 5 will go here because it has 2 machines here, only 1 machine here. So, part 1, 4 and 5. So, it creates one more intercell move with 4 and 5. Part 4 goes to machine 5. Part 6 has 1, 2, 3, 4. So, 1, 3, 4 are here, 2 is here. So, part 6 will go here and one intercell move is created, part 6 with machine number 2. Part 7 requires 2, 5, 6. 2, 5, 6 are all here. So, part 7 will go here. Part 8 requires 2, 5, 6. Part 8 also will go here. So, instead of creating another Jaccard similarity coefficient matrix for parts and carrying out a hierarchical cluster analysis and identifying the solution with 2 groups, we now have groups that are created using this particular rule. This rule is fairly intuitive because once the machine groups are known, each part will visit the machine group or will be attached to the machine group where it has maximum machines that it is visiting. We may encounter a situation where right now we do not have that in this example, but if there was we could have a situation where a part could visit, it may require 4 machines, 2 of them may be here, 2 of them may be here. For example, if we have a machine, if we have 7 machines and let us say 1, 4 and 5 are here, 2, 3, 6 and 7 are here, and if there is a part that requires 1, 2, 3 and 4, if it requires machines 1, 2, 3 and 4. So, here it has 2 machines, here it has 2 machines. So, based on our rule it could go here or it could go here. Either way it will create 2 intercell moves. But in such a case we will assign it, if there is a tie based on this, then we will assign it to a smaller sized group. So, it will go here instead of going here. So, there are 2 rules. Rule number 1 is a part will be assigned to a group if it has all the machines in that group. So, intercell move created will be 0. The same rule extended, the part will visit or will be assigned to a machine group where it visits maximum number of machines, so that the number of intercell moves created is minimum. If there is a tie, then the part will be assigned to the group which has the smallest size. So, here the size is 3, here the size is 4. If there is a tie, then it will go to this group. So, there are 2 important rules. Part will be assigned to a machine group where it visits maximum number of machines, and in the event of a tie it will be allocated to the smallest sized cell. Further ties can be resolved arbitrarily. So, we could use this rule to create this solution with part families 1, 4, 5, 6 and 2, 3, 7, 8 with 4 intercell moves from this solution. We also observe that this actually is the final solution with part families. The group 1, 3, 4 has 1, 4, 5, 6, you can see that in the picture, it has 1, 4, 5, 6, and the machine group 2, 5, 6 has parts 2, 3, 7, 8, which you can see there. The 4 intercell moves, part 1 to machine 6, part 4 to machine 6, part 5 to machine 5. So, let us check that in the previous picture. So, part 5 requires machines 1, 4 and 5. So, part 5 will go to this group with 1 and 4, and there will be an intercell move for part 5 to machine 5, and the fourth one part 6 to machine 2, they are all shown in red color. So, this way, using this rule we can now assign parts to available machine groups. The rule has 2 important aspects. Each part will go to the machine group where it visits maximum number of machines, and in the event of a tie it will be assigned to a group which has smallest number of machines. So, we can call this rule as a part assignment rule, and use this rule to assign parts to given machine groups. We will revisit this part assignment rule in the context of clustering later. So, this way we can use the hierarchical cluster analysis method initially to form machine groups, and then use the part assignment rule to assign parts to existing groups to minimize intercell moves. Now, we have not answered one question, which is what is the best number of groups that we should choose. This solution from the hierarchical clustering started with all of the machines as one group, and from there we had 1 3, then 1 3 4, these were the 6 solutions we got for number of groups varying from 6 to 1. So, from here we got, when we assigned part families, we did for this solution and then we got 4 intercell moves. It is also very obvious that if we have all of these into a single cell, if we have all of these into a single cell, then all the parts will go to only one group and there will be 0 intercell moves. And obviously this will have maximum intercell moves. For a given number of groups, the part assignment rule is able to give us a solution with minimum intercell moves, but then we can apply this part assignment rule to all these 6 and we will observe that this will have 0, this will have maximum. So, if we are going to let this help us choose the correct number of groups, then we will make the mistake of choosing this because this will have 0 intercell moves. So, we need other criteria to fix the number of groups if we do not, if we have not decided this a priori. Otherwise, it is good to solve the problem with known number of groups, so that we can get the corresponding machine groups and the part families from here and we minimize the intercell moves. Now, there are other measures which we can use to actually try and find out the best number of groups. So, when the problem is looked at from a theoretical perspective as to what is the optimum number of groups, then we should adopt different criterion to choose the best one. But if we look at this problem in the context of cell formation, now we should look at it in 2 ways. One is, it is a practical problem, therefore, we would assume that the user or the person from the factory or who is going to apply this technique will have a good idea as to what is the number of groups that is required. Once that is conveyed by the user to the decision maker, then we could go back and choose that this looks like the best number of groups, that is 2. For 2 groups, this is the machine cell configuration, this is the part family configuration, and we can do that. The other thing is, we could compute this and not make a decision based on this. We could see, for example, these 2 are extreme points, therefore, we will not be considering these 2, we will be considering in this range. Now, we can show each solution to the decision maker with certain number of intercell moves, obviously increasing from here to here, and let the decision maker choose the number of groups required. And for the chosen or given number of groups, we can provide a good solution that minimizes the number of intercell moves. Now, with this we move to a non-hierarchical clustering algorithm and try to understand some aspects of non-hierarchical clustering. Now, as we did in the hierarchical clustering, we again go to an example where we consider points on the board or on a plane and then explain the non hierarchical clustering algorithm and then relate it to cellular manufacturing like what we did. So, let us assume that we have 5 points here. So, we call them 1, 2, 3, 4 and 5. Now, let us assume that we need to create 2 groups in this. This is the difference between the hierarchical approach and the non hierarchical approach. Here we are initially deciding what is the number of groups that we want to create. Now, in order to create these 2 groups, let us try and identify 2 points which we call as seed points S1 and S2. We call them as 2 seed points S1 and S2. Now, the moment we fix these 2 seed points, now we have to group the remaining 5 points into the 2 seed points. So, we take point number 1 which is to be grouped and find out to which seed point it is near, or we find out the nearest seed point to point number 1. So, that happens to be S1. So, point number 1 will go to S1. Which means we will find out the distance between 1 and S1, 1 and S2 and allocate it to S1 based on minimum distance. Similarly, point 2, again we find the distance between S1 and S2 and allocate point 2 to S1. So, point 3 will automatically go to S2, point 4 will go to S2 and point 5 will also go to S2. So, a 2 group solution for this will be 1 and 2 belonging to one group, 3, 4 and 5 belonging to the second group. Now, the only important consideration here is in the choice of these seed points. An incorrect choice of these seed points can actually give us sometimes poor solutions. For example, instead of choosing the seed points the way we did, one of them here and the other one here, if we had chosen the first seed point here and if we had chosen the second seed point here, then what happens to the groups? Now, 1 will again be attached to this one because this is nearer, 2 again will go to this, 3 again will go to this, 4 will go to this and 5 will go to this. So, one seed point would attract all the 5, the other will not be able to attract anything. So, the groups will not be 1, 2, 3, 4, 5, but it will be 1, 2, 3, 4, 5 and blank. So, we have to make sure that the seed points are well chosen, so that the solution is good. Now, one of the ways of doing that is by not keeping now in the 2 previous examples we have chosen seed points which are actually different from the points themselves. So, now if I want 2 groups, if I choose 2 out of the 5 points themselves as seed points, then let us see what happens. Now, this 1 also becomes, let us say S1 and say 4 also becomes S2. So, now we look at 1 between 1 and S1 and between 1 and S2 and then put point number 1 to the seed which has minimum distance. So, distance between 1 and S1 is 0 because 1 is S1. this is a positive. So, 1 will sit on S1. 2 again I will see the distance between 2 and this and 2 and this. So, 2 will go here, 3 will go here, 4 will sit on itself and 5 will go here. So, now I have correct number of, now we have the correct solution because of a good and correct choice of seed points. Now, we understand that choosing the seed points from among the given points helps us in one thing, that point will get attached to itself and therefore, we will not have what is called a null cluster. In the previous case, when we picked one here and one here, we had a null cluster. The second seed was not able to attract any point. So, one of the ways of overcoming the null cluster is by having points themselves as seed points. So, now instead of choosing S1 here and S2 here, if we had chosen S1 here and S2 here, now what happens? Now, 1 will get attached to itself, 2 will get attached to itself, 3 will go to 2, 4 will go to 2, and 5 let us say will go to 1. Let us assume this is shorter, or say 5 will go to 1. Now, again we do not have the correct solution, because we know that based on distances 1, 2 and 3, 4, 5 is the correct solution. So, not only should the seed points be the given points themselves, the seed points should also be sufficiently far away from each other, so that they are able to attract points that are closer to them and therefore get good groups. Therefore, if we want to choose 2 seed points here, if I want to choose 2 seed points here, I would prefer to choose 2 points which are farthest from each other as 2 seed points. So, my seed point choice will become 1 and 4, which would give me a group 1, 2, 3, 4, 5. So, the rule is keep the seed points as large or as far away as possible, keep the distances as large as possible. So, one of the ways of doing this is by, when we know the number of groups, identify as many seed points as the number of groups, keep or make the given points themselves as seed points, and choose seed points such that they are sufficiently far away from each other. So, these are the basic rules. Now, let us apply this basic rule to the cell formation problem, the same example, and try to see what happens when we create groups. So, let us go back to the same machine component incidence matrix, which is this, and now we need a distance matrix. Now, the Jaccard similarity coefficient matrix is given here. In the previous lecture, we defined a dissimilarity or a distance. So, dissimilarity was defined as distance or dissimilarity between rows I and j is given as summation over k absolute value. So, if we take rows 1 and 2, row 1 has 1 0 0 1 1 0 0, row number 2 will have 0 1 0 0 0 0 1 0 0 row 1 has 1 0 0 1 1 1 0 0, row 2 has 0 1 0 0 0 1 1 1. Now, aik minus ajk. So, if you have a 1 0 pair or a 0 1 pair, the absolute value is 1. If you have a 1 1 pair and a 0 0 pair, the absolute value is 0. So, we should look at all the 1 0 or 0 1 pairs and add them. So, 1 2 3 4 5 and 6. So, D12 will be equal to 6. So, this way we can create a distance matrix, assuming that each of these rows or machines are points in an 8-dimensional binary space. So, if we construct such a distance matrix, we will get this matrix. The 6 that we computed between 1 and 2 is here. Now, we have to, now let us assume that we need 2 groups for which we need 2 seed points, and we said the seed points have to be the points themselves. So, the maximum distance is between 3 and 5, maximum distance is between 3 and 5. So, row 3 and row 5 or machine 3 and machine 5 act as 2 seed points. So, they act as 2 seed points with, this is the seed points, 3 and 5 act as 2 seed points. Now, look at machine 1. Machine 1 has minimum distance with 3. Now, we have to find out the distance between machine number 1 or row number 1 with the seed points 3 and 5 and assign it to the seed where it has minimum distance. So, 1 to 3 is 1 from the picture and 1 to 5 is 7 from this picture. So, 1 has minimum distance with 3 and therefore, machine 1 will go here. Machine number 2 is not assigned. So, 2 to 3 distance is 5, 2 to 5 distance is 2, it goes to minimum distance, 2 to 5 distance is 2, 2 is here. Machine number 3 is already a seed, so it will go to itself. So, I can write again 3 here because 3 will go to itself. Machine number 4, 4 to 3, the distance is the same as 3 to 4, which is 2, 4 to 5 is 6. So, 4 to 3 is 2, 4 to 5 is 6, it will go to 3. So, 1 3 4. Five is a seed, so 5 will go to itself. So, 5 will go to itself. 6, 3 to 6 is 5, 5 to 6 is 3. So, 5 to 6 is smaller, so 6 will go to 5. So, now we have a solution which has 2 machine groups with 1 3 and 4 as 1 and 2 5 and 6 as Now we have to do the question of part assignment. Now we could go back to this matrix and quickly do the part assignment. We actually observe that the solution is the same that we got for the hierarchical clustering. Therefore, the parts assigned will be the same if we apply the part assignment rule. Nevertheless, we repeat it. So, part 1 visits 1, 3, 4 and 6. So, part 1 will come here with 1 intercell move. Part 2 has 2, 5 and 6. So, part 2 will come here. Part 3 requires only 5 and 6. So, part 3 will come here. Part 4 requires 1, 3 and 6. So, part 4 will come here, another intercell move here. Part 5 requires 1, 4 and 5. So, part 5 will come here, third intercell move. Part 6 requires 1, 2, 3, 4. So, part 6 will come here with the fourth intercell move, 6 to 2. Part 7 requires 2, 5, 6. So, 7 will come here. Part 8 requires 2, 5, 6. 8 will come here. So, we have the same solution with 4 intercell moves, and we have seen a non-hierarchical clustering algorithm. The only thing that we need to do is, we were able to pictorially show the seeds in the earlier case, because these points were points on a 2 dimension. So, we could show the seeds, but then we cannot show the seeds in this case. We will now say that 3 and 5 are the seeds, and the rest of them with minimum distance with 3 and 5 will automatically go. Another way of doing it is by saying that row 3, which has 1, 4 and 6 components. So, seed S1 can be shown as 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, and seed S2 is 5, which is 0, 1, 1, 0, 1, 0, 1, 1. These are the 2 seeds. Now, if we take point number 1 or row number 1, we are taking 1, 0, 0, 1, 1, 1, 0, 0, and we are finding the distance between that point with this, that point with this, and wherever the distance is minimum, it gets allocated. Now, we can compute the distance, or we can keep the distance matrix computed like this and simply use the distance matrix to find out which seed to which it has minimum distance. So, this algorithm that we have seen is a non-hierarchical clustering algorithm. Non-hierarchical clustering algorithm. Now, we have used our part assignment rule to create part families for a given number of machine cells. Now, let us also try to understand the part assignment rule as a clustering rule. Let me explain that. Now, let us go back and let us write just these two machine groups 1, 3, 4, 2, 5, 6. Now, when we looked at the part assignment rule, we said that part 1 requires 1, 3, 4 and 6. So, maximum is 1, 3, 4 here, and it will create one intercell move. Now, what we can do is, now there are 8 parts. Now, the part assignment rule can be seen as another clustering way by which these 8 parts, which are 8 points, looking at the transpose of the matrix, each part can be seen as a point in a 6-dimensional binary space, 0, 1 space. Now, the part assignment rule can be seen as another clustering rule to cluster these 8 parts around the two groups, and putting each part into the group which has smallest distance. The way I introduced the part assignment rule, I introduced it as a way by which you take a part and put it into a group where it visits maximum number of machines. Now, I am going to modify this, redefine the part assignment rule again in the context of clustering, and show how it is actually a way to cluster these 8 parts to these two groups. Now, once we have formed these two groups, let us say that these two groups are represented by 2 seed points. The group itself is represented by a seed point. So, this will give a seed point S1 with 1, 0, 1, 1, 0, 0, and this will give a seed point S2 with 0, 1, 0, 0, 1, 1. Now, 1, 3 and 4 gives me a seed point with 1, 3 and 4 positions having a 1 and the other positions having a 0. 2, 5 and 6 will give me another seed with positions 2, 5 and 6 having 1 and the rest of them having 0. Now, the nice thing about these seeds is that since each machine will figure only in one group, each column will have one only in one place. So, now I go back and take the first part. The first part is 1, 0, 1, 1, 0, 1. So, the first part P1, let me call it, look at the column per se, is 1, 0, 1, 1, 0, 1. Now, I find the distance between this and the distance between this and this. So, distance between seed S1 and part P1 is equal to the number of 0, 1 or 1, 0 pairs will constitute a distance of 1. So, this is a 1, 1 pair, 0 distance, 0 distance, 0 distance, 0 distance, 0 distance, 1 distance. This will give me 1 distance. So, distance is equal to 1. Let me repeat, 1 and 1, it is a 1, 1 pair, distance is 0, 0, 0 pair, distance is 0, 1, 1 pair, distance is 0, 1, 1 pair, distance is 0, 0, 0 pair, distance is 0, 0, 1 pair, distance is 1. So, total distance is 1. Now, D S2 P1 is equal to 0 1 pair distance is 1, 1 0 pair distance is 1. So, total 2, 0 1 pair 3, 0 1 pair 4, 1 0 pair 5, 1 1 0. So, total distance is 5. So, distance between part 1 and seed 1 or group 1 is 1, distance between part 1 and seed 2 or group 2 is 5. Part 1 will go to the group which it has minimum distance. So, part 1 will go here. Let me show one more illustration and not all the 8 of them. Let me show one more illustration to understand this. So, let us take P2, except that I am not writing them as column vectors, I am writing everything consistently as a row vector. One could write it as a column vector and map it. So, part 2 is a 0 1 0 0 1 1, 0 1 0 0 1 1 is part 2. So, D S1 P2 is equal to 1 0 pair 1, 0 1 pair 1 plus 1 2, 1 0 pair 2 plus 1 3, 1 0 pair 3 plus 1 4, 0 1 pair 4 plus 1 5, 0 1 pair 5 plus 1 6, 0 0 0, 1 1 0, 0 0 0, 0 0 0, 1 1 0, 1 1 0 identical. So, distance is 0. So, part 2 will go to seed 2 or group 2 with which it has minimum distance. So, part 2 will come here. Like this we can complete it, we will get the same solution 1 4 5 6 2 3 7 8. So, our part assignment rule is essentially a clustering procedure where the part is assigned to the group with minimum distance. So, the same rule can be looked at in two ways. If we say that each part will go to the machine group where it visits maximum machines, automatically it will have minimum distance with that group. So, in simple terms, the part assignment rule assigns parts to machine groups where it visits maximum number of machines. Subsequent rule qualifies it better to say that in the event of it being equal or there is a tie, it will visit the group with the smallest size. It is seen as a clustering way by which part is now seen as a vector with zeros and ones, and each of this group can be written as a seed, and then the part vector is mapped with the seeds, and then you find out which seed it has minimum distance and the part goes to that seed. So, this is the same as finding out which group it has maximum machines or which group it has maximum similarity, and it goes to that group. So, the part assignment rule is a very simple way of clustering parts or assigning parts to machine groups. So, this is how a non-hierarchical clustering algorithm works for cell formation. So, given number of groups, first compute a distance matrix based on this distance rule. Now, here the distance matrix is given, similarity is not given, based on this rule where Dij is equal to summed over k absolute value of Aik minus, based on this rule. Find out as many seed points as the number of groups required. If more groups are required, make sure that the seed points distance amongst the seed points is maximum. For example, if we need 3 groups and if we had chosen 1, 3, 5 and 1, let us say, then we have to ensure that distance between 3 to 5 is large, distance between 1 to 5 is large, distance between 1 to 3 is also large. So, that is where the real difficulty comes in finding out the correct seed points, because the seed point should be chosen such that the distance amongst them, all the distances are large. If seed points are chosen that 2 of them are nearby, then they will attract points in a different manner and we may not get the correct set of groups. But then choose the seed points, cluster the machines or rows with the seed points, get machine groups, either apply the part assignment rule or cluster the parts around machine groups the manner that it was described here, get the part groups, and while getting the part groups compute the intercell moves for a given number of groups. We also have to bear in mind that after this we have to find out ways by which the intercell moves can be reduced, so that the implementation can be carried out. But the moment we start analyzing these with 0 1 matrices, we will be concerned about minimizing the intercell moves. But we have to understand that the problem does not stop there. We have to now try and minimize the intercell moves through the ways that we had described earlier, which is operation subcontracting, part subcontracting, machine duplication, change in process plans, etc. Now that we have seen some algorithms for cell formation, now do they provide the best solution, or is there scope for using optimization to try and get the best solution? Can we formulate these problems as proper optimization problems? So far we have seen them as clustering problems. Can we formulate and solve them as optimization problems? That approach we will see in the next lecture.